In the electrical instrument, again we are going to learn about the meter bridge. So it is simply it is a simple electrical instrument which works on the principle of heat-stone bridge to calculate the resistance of unknown resistor. A diagram of heat-stone diagram of a meter bridge is shown here. These are thick metallic strips, generally made of copper, and this is a manganese or constantine wire of 1 meter length. This is a jockey connected to the point P, and this is a galvanometer also to see the current flowing or not. This is external battery, and this is the key to on the circuit or off the circuit. Now construction. The construction is shown in the figure. 1 meter long constantine or manganese wire. Manganese wire is connected taut between A and C. One end of galvanometer is connected to point B and other end with a jockey which can slide on the wire. R is a unknown resistance and S is a standard known resistance. Here R is the this resistance is unknown and this is known resistance. We have to calculate this value. Working. We slide the jockey on the wire until there is a no deflection. After switching on it, so that current should flow in the circuit. We slide the jockey on the wire until there is no deflection in the galvanometer. This is called balance condition. Theory. Let L equals to position of jockey from A. That is from A. This is the position of jockey from A, and this distance is L when there is no deflection in the galvanometer. And let 100 minus L is the position of jockey from C. Let R dash be the resistance of the wire per unit length. R dash is the resistance of wire per unit length. Then resistance of wire of length L will be R dash into L. Hence resistance of wire of length 100 minus L will be R dash into 100 minus L. As the heat-stone bridge is balanced, the corresponding diagram is drawn here. This is R, this is S, this is connected galvanometer at point B. This is point B, and this is the jockey point where there is no current in the position of jockey when there is no current through the galvanometer. And this distance is R dash into L. So this distance is L, and so here corresponding resistance is R dash L, and this distance is 100 minus L, which corresponding resistance is R dash into 100 minus L. R dash is the resistance per unit length. So multiplying length we will get the resistance. Now when we know that when the heat-stone bridge is balanced, we can write R by S equal to R dash L by R dash 100 minus L. So this implies R by S equals to L by 100 minus L. Hence R equal to S into L by 100 minus L. This is our formula to calculate the unknown resistance R using the meter bridge. Using this formula we can calculate the unknown resistance. Again we have R by S equal to L by 100 minus L. This means that R 100 minus R into L equal to S into L. This implies 100 R equal to R plus S into L, or hence L equal to 100 R by R plus S. From this formula, that is we have calculated here length when it is in the balance condition. It is equal to the 100 R by R plus S. From this formula it is clear that if we connect another resistance with S, that is resistance with S in series, then balance point will shift towards left, that is L decrease, because when we connect a resistance, the resistance will increase, and so the value of L will decrease. From this formula it is clear. Again, second one, if we connect another resistance with S in parallel, if we connect S in parallel, then equivalent resistance will be less than S, and so L will increase. Resistance with S in parallel, then balance point will shift toward the S, towards right, that is towards C. That is L increases. In this case, L increases. This is the concept for increase and decrease in the balance. Here it is clear from the this formula that if we connect a resistance parallel with S, then the value of denominator will increase, and so L will be increase, and so L will decrease. So jockey will shift towards A. And again, if we connect another resistance with S in parallel, if we connect a resistance with parallel with S, then the denominator will increase, and so decrease, and so L will increase. In this case, point, and so because L is increasing, so point will jockey will shift towards C, that is L increases. So this was the concept of meter bridge. Now let's see about potentiometer. It is also a measuring device. It is used to compare EMF of a cell. Potentiometer, it is a versatile electrical instrument which is used to compare the EMF of the cell and also to find the internal resistance of the cell. It consists of a long uniform manganese or constantan wire AB fixed on a wooden board as shown in the figure. This is a wire which is connected like this. This arrangement is made to make smaller the device. This is a metallic thick strip, and this is again metallic thick strip. These are connected, and current can flow like this. These are thick so that its resistance should be less in compared to this length. And it is connected to a external battery E of EMF E, a variable resistant or rheostat R, RH, and a K to open, to on and switch off and switch on the circuit. And this length is of 400 centimeter from the wire length, that is this length of this total length is of 400 cm. And again this point is connected with E1 and E2 which EMF is to be compared, and it is a switchboard, two-way switchboard. When once we connect to it and one point, and in other way we can connect to another point to change the loop. And it is also connected with the galvanometer to see the current flowing in the and this is jockey whose position is given, that is at 1 and at 2. Now principle. It works on the principle that potential difference across any part of a uniform wire is directly proportional to the length of that portion. When a constant current flows through the wire, that is V equals to IR, and I into R is given by rho into L by A, equals to I rho by A into L, and this value is constant, so V proportional to L or V equals to KL we can write. That is potential difference is directly proportional to the length of the wire. First case, to compare the EMF of the cells. To do this, first close the key K. This is making closing this K to start the current flow or switch on the circuit. And Connect the two-way K 1 and 3. Now slide the jockey on potentiometer wire. Consider at N1 no deflection is shown in the galvanometer. Here we see that first it is closed, so that current should start to play, and then we jockey 1, this switch is connected to 3, so that current can flow from this E1, and it is open, so that not current does not flow from the E2. Now there is deflection in galvanometer. We are seeing a deflection in, and this is connected to a jockey. Now we have to slide the jockey on the wire, and see, and we have to see at what point the current through the galvanometer becomes 0. That is, there is no deflection in the galvanometer, and after sliding at point N1, we see that there is no current from the galvanometer. That is, deflection in the galvanometer is 0. Let in this condition, when there is no deflection in the galvanometer, L1 is the length of the wire from A to N1. That is, now consider RAN1 is the resistance of the wire of length L1, AN1, and VAN1 is the potential difference between points A and N1. If phi is the PD, potential difference per unit length of the wire, then potential difference over length L1 is phi into L1. Hence VAN1 equal to phi into L1. This is equation 1. Now the equivalent circuit diagram is shown in the figure. This is the external battery, this is the rheostat, this is the key which is switch on, and this is the wire. We have this is wire which was connected with the help of metallic strip. We are showing only wire here, a schematic diagram, and this is the our two-way switch which is connected. This is the E1 cell 1 whose EMF is E1, and it is connected to the switch 3, two-way switch. One is connected to 3, so E1 can be in the work, and this is the galvanometer where we have to see the deflection. Let I current is flowing through the wire AC. In the when there is no current in the galvanometer, in this case we are considering that I current is flowing in the wire. Then applying KVL in A13GN1A, A13GN1. In this loop we have to apply KVL. So we have minus of E1 plus I into R AN1 equal to 0. Here we are going from higher to lower, so lower minus higher will be negative, so minus E1, and here we are going from lower to higher, so it will be positive. So I into R AN1 equals to 0, where R AN1 is the resistance from A to N1 wire of this part. This supply minus E1 plus VAN1 equal to 0. We have calculated this value VAN1, and equals this supply minus E1 plus phi L1 equal to 0, or E1 equal to phi L1. This is equation 2. Similarly, when key 2 and 3 is connected and to be the position of the jockey where no deflection in G is found, then we have E2 equal to phi into L2. This is equation 3, where L2 is the length of the wire from A to N2, dividing 2 by 3, E1 by E2 equals to L1 by L2. Thus we can compare the EMF of the two cell by using this method. Here it is given E1 by E2 equal to L1 by L2, and corresponding diagram is shown here. When this is the battery E2, cell E2, and now switch 2 and 3 is connected, so that current flow through E2 initially, and we slides the jockey point on the wire, and at N2 there is no current through G, and using above concept we have calculated value of E2 equals to phi into L2, so E1 by E2 will be L1 by L2. next will be in the next topic we will learn about the how to calculate internal resistance with the help of potentiometer.